In the last section, we learned an optimization method for finding min and max of z equals f of x comma y, including the special situation if a region is given with boundary, and we could check what happens on the boundary. In this section, we're going to learn an entirely different optimization method, which applies really in different settings. To warm up, let's consider the following situation. Maximize f of x comma y equals x to the 7th, y to the 9th, subject to a constraint, another function called g of x comma y equals 3, where g of x comma y happens to be the function x to the 4th plus y to the 4th. So let's take a look at the following link first. What we're looking at here is a bunch of level curves for this x to the 7th, y to the 9th thing, right? So we want to know how big or small this can get, but we are restricting ourselves to the situation where x to the 4th plus y to the 4th is equal to 3. So where x to the 4th plus y to the 4th equals 3 is all along this red curve. So somewhere along the red curve is where we need to be. And currently, we're looking at output 2. And it looks like there's a spot right here and right there. But we could do better than that. So what point on the red curve looks best? It actually happens to be right about here. So there's a point on the red curve where the where the z value appears to be 5.2. If we were more greedy and wanted the z value to be 6.2, well, that's not good because that's not a point on the red curve anywhere. So we want something that looks like this. So we slowly increase k to see which level of set. It turns out that the largest output of the function f occurred when the gradient of f and the gradient of g are parallel vectors. So you'll see the gradient is going to end up pointing in this direction for both of those. So this is a matter that we don't want to dig into with too much detail here, but this is always going to occur. And so there's a general fact that the optimum is going to occur when there exists a scalar such that the gradient of f is equal to lambda times the gradient of g. So in other words, the gradient of f and the gradient of g, which are both vectors, they need to point in the same or an opposite direction. So they're parallel vectors. Okay, because these vectors must be parallel, if x comma y is optimal for f, yeah, this lambda must exist. And so based on this, we create this thing called the method of Lagrange multipliers. Let f of x comma y and g of x comma y be two functions, and k is going to be a given constant. Okay. If the task is to maximize or minimize the function f, subject to the equality constraint that the function g must equal k. So we're only looking at x, y's where the output to the g function would be the number k. Then here's what we're going to do. We're going to find all x, y, and lambda such that the gradient of f is equal to lambda times the gradient of g. And then amongst all of the x, y, lambda combinations that we get, we actually won't need lambda anymore. It's just that's the number that scales the gradient of f and to be the gradient of g or vice versa. We're really just going to take all the x, y's we get, dump the lambdas, take all the x, y's we get, and evaluate f to see which is the largest z value and which is the smallest z value. Just some notes. Yesterday's topic was certainly tedious, but once you know yesterday's recipe, it's not too bad overall. Conceptually, you'll see that this new method isn't so bad, really, in terms of just conceptually what's happening. The thing that's actually really strange is that the algebra is surprisingly challenging for these questions. Often you have problems with 5 equations and 5 unknowns, so just be patient, just be persistent, just work through the algebra steps. If you feel stuck, just go back and look at, wait, what equation did I not use? You might try to draw arrows from one equation to another, just to make sure you've got a good roadmap of which things got used and which things didn't. So keep re-examining previous equations, keep substituting, don't give up, something is going to work out.